Hi, this is going to be my presentation on the simple harmonic motion, waves, and sound unit. First, the difference between periodic motion and simple harmonic motion. Periodic motion is something that happens over and over again with a period. Simple harmonic motion would be something that actually goes around the same path again and again and again. So if I had a spring with a mass on it and I stretched it out and let it go, that mass will move from down here to up here, back and forth, and that is simple harmonic motion. Actually, if I were to swing an object in a circular path, sorry, that's a poor drawing, again, and it went around in the circle again and again, that would also be simple harmonic motion because it travels through the same path over and over again. Hooke's law, speaking of springs, Hooke's law says that if I have a spring and I hang a mass from that spring, then the force that the spring exerts, now Fs is the force that the spring is exerting upward on that mass, is equal to minus kx, where k is what we call the spring constant. We knew that from the energy unit. K is the spring constant, S-U-N-S-T-A-N. Stunt, I didn't spell that right. S-T-A, there we go, sorry. K is the spring constant and x is the displacement. So if that spring had been this long, and then when I hung the mass on it, the spring stretched down to here, this distance x, that's the displacement. Now let's talk about that negative sign. Just always use the negative sign, but what it really means is that the force exerted by the spring is always in the opposite direction of that displacement. The spring is going to pull up on that mass, so the spring force is up. The displacement, it moved from here down to there, so the displacement is down. So that negative sign simply means the spring force is opposite into the direction of the displacement. For oscillating springs, the period, this would be an oscillating spring. If I stretch this and let it go, it would go back and forth and back and forth. The period depends only on the hanging mass and the spring constant. The period can be calculated by 2 pi times the square root of the mass divided by the spring constant. It's a pretty simple calculation. Just plug stuff in. If you have a pendulum, the period of a pendulum only depends on the length of the pendulum and gravitational acceleration. So if I have a pendulum, it doesn't depend on the mass of the pendulum. It doesn't depend on, well, the amplitude actually has to stay rather small for this to work, like under 30 degrees. But it depends on just the length of the pendulum and gravitational acceleration. So the same pendulum on the moon, because gravitational acceleration on the moon is different, would have a different period. This is how you calculate the period of a pendulum. A wave. What exactly is it, and what is traveling and what's not traveling? Waves are disturbances. They're energy that moves from one place to another. It is energy that travels, not the medium, E-N-E-R-G-Y. I'm not spelling well today. What is not traveling? The medium. And what do I mean by the medium? It's the stuff the wave is traveling through. So water can be the medium. Right now I'm talking, the air is the medium. The air molecules are not traveling. They're moving back and forth around their rest position. They're oscillating, vibrating, but they are not moving from one place to another. The energy is. There are 2 primary types of waves, electromagnetic and mechanical, and we'll talk about electromagnetic waves later when we talk about light. There's another unit, and we'll talk about this a little bit later. Right now, we're talking about mechanical waves. Mechanical waves have to have a medium to travel through. Light and other electromagnetic radiation does not. There are 2 types of mechanical waves, transverse waves and longitudinal waves. Transverse waves are waves in which the particle displacement, or a medium particle displacement, is perpendicular to the wave motion. So if I have a string, and the string looks like this, and I were to pluck the string, pull it down, I would create a wave pulse that would look like this, and it would travel, and every little particle sitting on the string would move down and then back to the rest position as the wave passed. So like if the wave is right here, then a particle that had been sitting right here is now displaced down to there. A particle that had been sitting here is displaced down to here. So the particle displacement is down and then back up, while the wave motion, the velocity of the wave, is to the right. So perpendicular. Displacement perpendicular to a wave. A stadium wave, okay, I've had a middle school teacher once argued that a stadium wave wasn't really a wave, and I can't say they're completely wrong, but it's a good example. If you're at the stadium and you're sitting in your seat, here's your seat, and you're sitting, and the wave comes by, you stand up out of your seat, and then you sit back down in your seat. And so your motion is up and then down, while the wave passes from person to person going this way. So I think a stadium wave is a good example of a transverse wave. So transverse waves, the particle displacement, the particles in the medium that move when the energy gets there, is perpendicular to the wave motion. So a longitudinal wave is a wave in which the particle displacement displace in a hurry and messing up. The hurrieder I go, the behinder I get. Displacement is parallel to wave movement. So imagine you have a slinky. If you take this little piece of the slinky right here and pull it back and then let it go, that energy is going to travel through the slinky, and what you're going to see is places where the slinky is spread out and places where the slinky is close together and places where the slinky is spread out, and so on. Sound is a longitudinal wave, and I'll show you a picture of a sound wave in a few minutes. These areas where the slinky is spread out are called rarefactions, R-A-R-E-F-A-C-T-I-O-N, here and here. And where it's smushed up, it's called a compression. So the stretched out parts, rarefactions, and the mushed together parts are compressions. And this compression travels, or the compressions and rarefactions travel in, see the wave is traveling in this direction, and the motion, if I were to tie a little ribbon around the slinky here, I would see the ribbon go back and forth and back and forth and back and forth, parallel to the direction of the wave travel. Circular waves happen when the particle displacement is circular, both parallel and perpendicular to the direction of wave travel. So if I have this particle, and instead of just moving up and down or side to side, it does both. If it's moving in a circle and then back to where it started, it has moved up and it has moved down and it has moved from side to side. So it's doing parallel and perpendicular motion at the same time. And so the particles travel in a circle. And if you do an internet search for that, you can see a good example is deep underwater. There are transverse and longitudinal waves, and a particle of sand would end up just going in a circle around and around. Basic wave vocabulary. Amplitude is the height of the wave from the equilibrium position. Frequency is the number of waves cycles per unit time, or cycles per second generally. A cycle per second is also called a hertz. The hertz is the unit for frequency, and that means cycles per second. Mathematically, it's actually seconds to the -1 power, or 1 over seconds. If you have to find the frequency of something and you're given how many times the wave happens in a certain amount of time, it's the number of times the wave occurs, cycles divided by the time. Wavelength is the distance between two identical points on a wave, and the symbol is the Greek letter lambda. It's made like that, kind of like a upside Y sort of. Period is the time required for one cycle. Period is how many cycles happen in a second, and frequency is how many cycles happen in a second. Period is how many seconds it takes for one cycle. And you can see from there that frequency and period are inverses of each other. So, for example, if the frequency is 2 cycles per second, or 2 hertz, then the period would be the inverse of that, would be 1/2 of a second. If 2 waves happen in 1 second, then 1 wave would happen in 1/2 a second. They are inverses of each other. So if you have one, you can easily calculate the other. Period is units of seconds. It's a time unit, and it's capital T is the symbol. So parts of a wave, amplitude is the distance from the equilibrium position to the maximum displacement. It is not from the bottom to the top, it's from the middle to the top. Wavelength is from any point on a wave to the identical point on the next wave. So the wavelength would also be the distance from here to here. Trough, the tops are crests and the bottoms are troughs. If you have a longitudinal wave, the compressions correspond to crests and the rarefactions correspond to troughs. And we'll see a good picture of that in a minute, and I'll point that out. For any wave, the speed of that wave in the material is the frequency times the wavelength. If you're given any 2 of these 3 quantities, you need to be able to find the third. So frequency would be velocity divided by wavelength, and wavelength would be velocity divided by frequency. So easy peasy calculation, but you need to be able to do it. Wave speed is a characteristic of the medium and only the medium. It is not a characteristic of the frequency. So for a given medium, if the wavelength of a wave changes for some reason, the frequency would also change to keep the speed the same. It's a frequent question that I see on tests is which travels faster, a high frequency sound or a low frequency sound. They travel with the same speed through the same medium. It is frequency independent. What happens to an amplitude of a wave while it travels? As it travels, why? The amplitude of a wave as it travels gets smaller because of energy dissipation. If you think about it, if this is a string and I were to pluck this string, to send this wave pulse down the string, well, that energy has to be used to move every particle out of its equilibrium position and back down to its equilibrium position. And so the energy gets used in moving those particles, and so as the wave travels, it's going to get lower and lower and lower. Amplitude is related to energy. The higher the energy of the wave, the greater the amplitude. And so the energy gets used, and so the amplitude gets smaller. The superposition principle says basically 2 things, that 2 waves or multiple waves can occupy the same space at the same time. And it says that the net displacement of the medium is equal to the sum of the 2 individual, we'll leave it to the 2 waves for right now, the individual displacements that each wave would cause. So let's go down here to constructive interference. Suppose in a medium, let that be a string, I have a wave pulse that looks like this, and it's moving that way, and I have another wave pulse that looks like this, and it's moving this way. Well, what's it going to look like when the 2 waves both get to right there? Well, because the wave displacements are both, in this case, positive, they're both above the equilibrium line, they will add together. The superposition principle says that the displacement is the sum of the displacements, and these would both be positive. And so this wave would make the medium move to here. This wave would make it move this much higher, so like up to here. So what you would have when both waves were there at the same time would be a displacement that looked like that. And because the displacement's bigger than the 2 waves were individually, it's called constructive interference. So you can probably guess what destructive interference will look like. If I have, there's my medium, and if I had this wave moving this way, and I had this wave with a negative displacement moving that way, well, what's it going to look like when they get to the same point? Well, this particle would move to here if the light blue wave got there by itself, it would move to here if the green wave got there. And this is a negative displacement, and this is a positive displacement. So they add, but they're opposite signs, so it's kind of like a subtraction. And so the resultant wave would be here. And that would, well, sorry, this is destructive, not total. Well, what is total? Sorry for the error here. What is total destructive interference? Well, it would be where the waves were on the opposite sides and had the same amplitude, but opposite, so they would completely cancel. So if I had a wave that looked like this, moving this way, a wave pulse, imagine plucking a string, and I had a wave that looked exactly the same, but on the, oops, that's the same color, isn't it? It did look exactly the same. Same size, but on the other side, then when they get to the same point, this particle would move this high if the blue wave came. It would move this low if the green one comes. And so the two energies, or the displacements cancel each other out, and you get total destructive interference, a zero displacement. Okay, standing waves. You've seen standing waves happen. If you pluck a guitar string, it sets up a standing wave. I'm going to go to this YouTube video quickly. We're not going to watch very much of it, but this guy's going to make a standing wave. Ooh.
So then a standing wave is where you pick a frequency that matches the length of the string in such a way that the waves created from my side of the string and bouncing off of Parker's coincide with each other and reinforce each other to create a standing wave pattern. The lowest frequency standing wave pattern is this one. It's called mode, M-O-D-E 1, or the first harmonic, or in other words, also called the fundamental mode. It's the lowest frequency mode that you can get in a transverse standing wave. If I double the frequency of that mode, I get the second harmonic, or second mode, and sometimes called the first overtone.
Okay, that's all we really needed to watch. So that standing wave pattern, when you shook it in such a way that that slinky vibrated like this, up and down as one full unit, that was the fundamental frequency of that slinky. It's also called the first harmonic. We call these points where there is no displacement, we call those nodes. And this point where we have maximum displacement, we call either a loop or an antinode. When he shook it faster, he got the second harmonic, same slinky, but it was vibrating with this pattern. Notice in this case, the wavelength of a wave is equal to the length of that string. And in this case, we had 3 nodes, and we have 2 antinodes. This is an antinode here, and this is another antinode here, so 2 antinodes. And that is the second harmonic. And you can count loops or count antinodes to know what harmonic it is. Antinodes happen when you have alternating constructive and destructive interference. Nodes happen where you constantly have destructive interference of the incident wave and the reflected wave. This is another picture as the harmonics get more and more complex. This is the first harmonic, just like we drew, with the whole string vibrating as a unit. The string length is 1/2 of a wavelength. And the second harmonic, just like we drew, the string length is equal to a wavelength. And all the way down here to the 6th harmonic, you can tell it's the 6th by counting the antinodes. There's 1, 2, 3, 4, 5, 6. So 6 loops or 6 antinodes, and you have the 6th harmonic. To find the frequency of the first harmonic, also called the fundamental frequency, you can use this formula, but you need to know the velocity and the the velocity and the wavelength. So the frequency of the fundamental frequency, or the frequency of the first harmonic, would be equal to the wave speed in that medium, so at how fast does the wave move on that string, divided by the wavelength. Fundamental frequency on a wave on a 2-meter long rope. Okay, so if it's vibrating like this and the rope is 2 meters long, then the actual wavelength would be 4 meters, because in the fundamental frequency it vibrates, the whole string length is a half of a wavelength. Find the fundamental frequency, 2-meter long rope traveling at 2 meters per second. So the frequency would be 2 meters per second divided by 4 meters. So it would be 0.5 hertz. This is that longitudinal wave picture I told you I was going to show. You can see the compressions and the rarefactions and how they travel through the materials. Sound is a longitudinal wave. It is a series of compressed air and rarefied or spread out low pressure air traveling from the source of the sound to the receiver. Sound can be made to look like a transverse wave, but sound is a longitudinal wave. Let's see. Sound can travel through solids, liquids, and gases. The speed of sound in air at 20 degrees is about 343 meters per second. To easily calculate the speed of sound in air given the temperature, and you will have to do this on quizzes and tests, just use this formula. It's not given in the content, but it works the same. It gives you the exact same answer. I double-checked with all the quiz and test answers. 331 plus 0.6 times the temperature in Celsius. So if it's 20 degrees Celsius, the speed of sound is going to be 331 plus 0.6 times 20. 0.6 times 20 is 12, and 12 plus 331 is 343 meters per second. And at minus 10, that'll be 331 plus 0.6 times negative 10. And so that's a negative 6 here. And so 331 minus 6 is going to be 325 meters per second. So it's way easier than another formula that you might see. Notice in air, in hot air, the speed is higher. In solids, these are solids, it's way faster than in a gas, and in liquid, it's kind of in between. So sound travels fastest in solids, slower in liquids, and slower still in gases. Loudness is how our ears interpret amplitude or intensity, energy, of the wave. Pitch is how our ears interpret the frequency. High frequencies are high pitches, low frequencies are low pitches. Humans can generally hear sounds in a frequency range from about 20 to 20,000 hertz. So anything above 20,000 hertz is called ultrasonic. Anything below 20,000 hertz is called infrasonic. Supersonic is when things travel faster than sound, so it's a totally different thing. Sound waves are more intense, have larger amplitudes and more energy close to the source. We said earlier that amplitude decreases as a wave travels. So the closer to the source, the greater the amplitude, the greater the intensity, greater the energy. So sound is louder closer to the source. That's why you hear things better when you're closer. It's an inverse square law, actually. So if you're twice as far away from the source, the intensity is only 1/4. If twice as far, that's 2 times. The inverse of that would be divided by 2. The square of that would be divided by 4. So the double your distance, you reduce the intensity to 1/4 of what it was. Okay, this may or may not show up for you on a test or a quiz. A decibel is a measure of sound intensity. It's a logarithmic scale. An increase in loudness from 50 decibels to 70 decibels would be an increase of intensity of 100 times. So the sound is actually 100 times louder if you go from 50 decibels to 70 decibels. Well, how did I get it? 70 minus 50, the difference in decibels is 20 decibels. Well, a decibel, that's 1/10 of a bell. The bell's the actual unit. And so divide by 10 to get a bells, and that's 2 bells. And each bell is a power of 10 difference in sound. And so that means it is 10 to the second times louder, or 100 times louder. Some other things that you need to know from this unit, very straightforward plug-in stuff. The intensity of sound can be calculated by dividing power by area. The threshold of the human humans begin hearing at about 10 to the minus 12th watts per meter squared, and the threshold of pain where things hurt when you hear the sound is about 1 watt per meter squared. To calculate relative intensity, you use this equation. You divide the intensity by the threshold of hearing. Take the log of that. That's log base 10. That's not natural log. It's the LOG button on your calculator. Multiply it by 10. That 10 converts from bells to decibels, and you'll get the intensity of the sound level in decibels. So if we look at these examples that you had to do if you looked at the content, calculate the relative intensity of a sound with intensity of 15,900 watts per meter squared. Well, here's the solution. 15,900 divided by 10 to the minus 12th, that's the threshold of hearing. Natural log of that, multiply it by 10, and you get 162 decibels. Here's another example. Find the relative intensity of a sound with intensity of 0.000145 watts per meter squared. Divide that 0.000145 by the threshold of hearing intensity, which is 10 to the minus 12th. Log base 10 of that, multiply it by 10, and you get 81.6 decibels. So it's a pretty straightforward calculation, even though that equation is a little bit scary. For Doppler effect, the Doppler effect is an apparent change in frequency due to the relative motion of an observer or a source. So it's when a sound sounds like it has a different frequency, but it really doesn't. I'm going to give you a really quick example of that. This is a little obnoxious, but it's a very, very short video. Okay, so it wasn't until, kind of right there at the end that you hear that pitch drop as the source is moving towards you, and then the source moves away and the frequency changes. So it's, again, kind of an intimidating looking formula, but it's very straightforward. The frequency that you hear is equal to the frequency times. Plain old V is the velocity of the wave, which would be the speed of sound in air. V0 is the velocity of the observer. If the observer is moving towards the source, then that is a positive value. If it's moving away from the source, it's negative. And if the observer is not moving, it's 0. And Vs is the velocity of the source. Again, it is positive if it's moving towards. Okay, if this is positive, then that negative stays negative. The Vs, velocity of the source, is negative if it's moving away from the observer. And so if this is negative, then it would make that negative be a positive. Two negatives would make a positive. But it's not what is that sign, it is what is the sign of the velocity of the source. And that is the end of this presentation.